So what we will do packing, but specifically we will do soft packing, and we will come to soft or probabilistic packing. And I will come to, okay, I need to.
Recording in progress.
Okay, and I will also, so I will come to hard or more deterministic packing, maybe in a few lectures, depending on how it goes. Okay, so before that, so first of all, I'm very sorry for all the, too many mails and everything, and also for very thankful to all of you for responding. That's really nice of you. This is not going to happen. It's just going to happen a few. I mean, so we will fix up some things today, and we will not, do too many emails or anything, and we'll fix up some slots. So this is not going to happen, but I just want to ensure that we get back on track. The last week was bad, and I was not able to hold the classes, so we will make up. If I understand correctly, if I count the 26th January as a class day, then I'm kind of behind by 6 classes. If I don't count the 26th January, I'm behind by 5 classes. But if I'm getting the count wrong, let me know. I'm not going to overload, but I'm going to just have 1 class extra per week or something of that sort. I also have office hours to ensure that it gets comfortable. My suggestion is that let's talk about all this at the end of the class, so that I get some material done, and then we can talk over all this. So having said that, let me get into soft or probabilistic packing. Any quick things you can let me know. I can pause, and then otherwise we'll go. I'll give around 5 minutes at the end, 5 to 10 minutes at the end to discuss all this. Also, I should let you know that the enrollment has been finalized. So there are many more students than I thought will be there. So I'm not going to change much, but I was thinking that I'll have some way of evaluation, but with the number of students increasing, it is not that easy. So to do with so many, but don't worry, I'm not going to change the basic structure much. I also have some plans for the projects and everything. So I'll let you know all this. So I'll begin with packing. I'll explain what's going on. So I'm assuming that you have done quite a bit of the homework, not that you have nothing at all. So let's kind of recall where we are. So it's been some time. So also you've done the homework. So let me just kind of. So we know what is our typical set.
So by the way, can I ask a question about the homework, or maybe at the end?
Homework, I'll have office hours.
Okay.
I will definitely have office hours. I can have it today. I can have it tomorrow. Not a problem. I'll have this office hours. So we have what is the individual typical set. So I have a distribution X. So I have a distribution X. I have a set X. I have a distribution PX. So I have a notion of individual typical set. So this is the set of all those sequences that are individually typical according to PX. That is the empirical distribution of the sequence is close to the probability distribution. Okay. Then we so that the size of this, and there is a very interesting object called the entropy, which tends to tell you a lot of things. So what is happening is that you have this big set, and there is a very small exponential set on which all the mass is getting concentrated. The rest of the mass is not, it's just gone. And it's uniform on that set. And that size has an exponential, that set has a very small exponent of growth. Okay, then when we go to 2 sets, X, Y, and we have a joint distribution, PXY. So now we can talk of the plain vanilla notion. The plain vanilla notion is the set of all jointly typical sequences. So that as you just think, you can we can just say, let's think of just Z as X cross Y. Then I just have one Z in some sense. I mean, it's a tuple, but you can be completely invisible. I mean, the X and Y, the separation of X and Y may be invisible to you, and you can just look at Z as X cross Y. And so then you have T delta N PZ. You can call it P delta N GZ. I don't want to do this, but just to make you, and get the math also. So this will be of size. There's nothing new here, but I'm just saying 2 times 2 to the power n of pxy. See, many times, I'm going to end up writing this as n h of pxy, xy, okay, h of xy. This is, the convention is that x and y are a pair of random variables with joint distribution pxy, and you're defining the entropy of this random variable as the entropy of the joint distribution. So, if you see this, don't, you'll have to relate this to this. Okay, there's some more interesting objects. So now I know that if I have pxy, I can also talk about the marginals. I can come and pull out marginals, px and py. And I observe that, okay, so this is also standard. Now I can be invisible to y. I mean, y could be invisible to me. And this I know scales as to power n h of x. And T delta N Py scales possibly as 2 power n h of y. I mean, not possibly, but it does scale as 2 power n h of y. So this is the individual typical sequences. So we also, if you have looked at the homework, you will observe the following, that if xn and yn are jointly typical according to the distribution. So the empirical distribution of the pair is close to the joint distribution. Then you can show that the empirical distribution of every letter of x is close to its marginal distribution, and every symbol in the yn sequence, that's empirical distribution is close to the py. Okay, so that's a very long way of saying in math essentially that if x and yn are typical, then xn is individually typical. That can't escape it out, and yn has to be individually typical. So we saw this. If you see this in the homework, you would have proven this. We'll give a solution to the homework. Okay. Now next is so we see this, and then we also, in the last class, I also mentioned, you look at joint entropy. So we define what is called now we can talk of a conditional distribution. Well, we don't talk of a conditional distribution. We then talk about a conditional jointly typical set, right? So conditionally typical set. So if I give you a sequence xn, then you can talk of all those sequences y, which if I pair with xn are typical. So you can look at this. So it's all those yn sequences that are so that if I pair it with yn, I end up in a typical set, T delta n pxy. Okay? So that is your conditional typical set. So it's like, you have, so the picture you should start to now develop in your mind is, you have this yn, you've chosen an xn, and you are fishing out all those yn sequences that are, when I pair it with the xn, they're going to be jointly typical. So this is kind of the thing. But also remember, if xn yn is jointly typical, then yn is individually typical. I'm asking for something more, right? So there are two things, right? So if I take an xn, first of all, if I take an xn, so we'll have let's start to do. Maybe I'll write a better picture. So I have this is my xn space. Okay, this is my yn space. Let's not go. Yeah, that's the xn space, yn space. Then inside this, there is a T delta n px, right? That's your T delta N Px. So, I mean, again, I've blown this up because I want this, the smaller circle to be big, okay? And this is my T delta Ny. Everything is with respect to one distribution. That is, I have a Pxy and everything is coming out of that. Now, what do? I first, suppose I take a sequence outside T delta Ny and I ask the question. So I study T delta N Pxy given Yn. So what do? I take a sequence here. This is, I'll call it Y tilde N. I take that sequence and I ask, give me all those Xn sequences. When I marry it with the Y tilde N sequence, they will be jointly typical. That set is empty, right? Because if there was such a thing, then you would have ended up getting an Xn and a Y tilde N that is jointly typical. But that implies that the Y tilde N is individually typical, but that's not true. So if you take a sequence outside the T delta N Py, then it doesn't have any conditional typical set according to our definition. There are different definitions of conditional typicality. According to my definition, it is not. These things don't, I mean, the different definitions really don't matter. If you look at Chisar and Kohn, I think a slightly different definition. If you look at Wild later, he will also talk about classical typicality. He'll also give a different definition. That definition is slightly different. The definition I'll stick to is this. They're all exponential. In the exponents, they're all the same. Okay. So it doesn't really matter. You're putting some polynomial sets, really doesn't matter. Okay. Now, if I'm more, if I get more interesting and I choose a Yn inside my typical set, in my T delta N Py, and then I ask this, this guy, T delta N Pxy given Xn, Yn given Yn, right? So then I get some ball here. But what I'm telling you is that ball is here. It is not here. Okay, it doesn't go outside the T delta N Px, because all those Xn's that you have to marry with the Yn, they have to be individually typical. So they will be in that set. Okay. And what we are, and then, what is the size? So we started asking the question, what is the size? And I think you would have shown this in the homework. I'm not exactly sure whether I did it in the class or in the homework. So this guy, which is a non-empty T delta N Pxy given Xn, this, so suppose, so I think this kind of slightly tricky, but suppose Xn belongs to T delta N Px. Okay, this then tells you that the set of all those sequences that are jointly typical, they are conditionally typical given the Xn. Okay, that is those Yn sequences that if I put it with the Xn, they'll become jointly typical. This is 2 power n h of y given x. See, I'm conditioning on the x here. Okay, conditioning on the x. So when I say this, so what now we come to, what is this h of y given x? This is essentially the average of the conditional entropies. Okay, so this is this y given x equal to a, and where h of y given x equal to a is just the entropy of the distribution when I condition on a. So this is what it is. I'm sure, I'm sure, some of you, it will be kind of new, but hopefully the homework has, kind of made your mind with this. These are objects that kind of get slowly confusing. Even with one, it is simple, but the moment you go to two, it could get confusing. So if there is another guy, let's say, y hat n, then that has another typical set that is going to, maybe overlap, may not be overlap. I'm not sure, but I'm just writing in general. Okay, it might not overlap. It may be disjoint, whatever. So that's all of this. So we observed a few inequalities. I'm going to write inequalities and inequalities. Okay. So one, h of x plus h of y, this is just algebra. H of x plus h of y given x is h of xy. And I'm putting all these things because this will give us an intuition as to what to expect in the packing and what we can do. Okay, so it's important to understand the sizes of these sets, very important. So that's why I'm kind of relating it with the inequalities, and then I'll go and prove certain things. Okay, this is the first thing. Second simple property you can show, we don't possibly we don't need this. Another thing that you will see, this is subadditivity. And it says that if I add h of x and h of y, I'm going to get a number which is greater than h of xy, generally. Okay. So, so this tells you that this is h of, so I can, on the right, I can use the first one and get this, right? So I can get this. So this tells me two inequalities, right? So it tells me that the uncertainty in x, I'm going to read it in English. The uncertainty in x, so x, the entropy of x is always looked at as the uncertainty in the random variable x. So how much uncertainty you resolve when you reveal it to somebody. Okay, so that's the way one should see it. We'll come to this interpretation. So h of x given y, I am, or you can write it as h of y less than equal to h of y given x, greater than equal to h of y given x. So what is the physics of this? What is kind of the the intuition behind this equation? So the left side is the uncertainty if you don't know anything. Okay, you just have you're completely oblivious to everything except the distribution. The distribution is not. Okay, and how much uncertainty does he have about x? That is h of x. Okay, that's the left hand side. The right hand side is for somebody who knows y. He doesn't know. So this object, I'm talking about this object. So somebody who knows y, how much uncertainty does he have about x? That happens to be h of x given y. And what this inequality is in physics saying, if I make it physically, what this inequality is saying is that the uncertainty reduces. So if I reveal something, if he knows y, his uncertainty about x is lesser than if he did not know y. Okay, so this is usually in information theory. This inequality is referred to as conditioning reduces uncertainty. Okay. Okay. I'm stating these inequalities because it's we will see these inequalities take a geometric shape as I go along. Okay, another third thing that this is something we will see in the classical, and you will see it will not happen in the quantum. So that's why I'm kind of separating the inequalities in this way. So later when you come back to this video, you will kind of recognize it. So we defined h of xy, right? So we went ahead and gave a definition. We went ahead and forced the definition, right? We said, take this, live with this, right? Just using the definition, you can show that h of x given y is greater than equal to 0. Just using the definition. What is this? This is the average of certain guys, right? This is the average of certain guys. Each of these guys is positive, so it better be positive. So that tells us something. So let's look at this. So what do we have? We have this, right? H of x plus h of x given y is h of xy. And the fact that h of x given y is positive implies that, so h of x given y is positive implies that h of xy is greater than equal to h of x, okay? Because the difference is h of x given y, okay? So h of x given y, sorry, h of x comma y minus h of x is h of x given y. So am I making a mistake? Yeah, I'm making a mistake. Stop me if you miss something or I'm going too fast. I'm trying to tell the physical intuition so that you can keep that in mind if the math is a little. I'll pause for just a minute or two, just a few seconds if there are any questions, but essentially this is what I've said so far.
Sir,
Yeah.
for the conditional typicality set definition,
Yeah.
can you give a definition which involves the empirical distribution, like the joint typical set or like that?
So yeah, I mean, you can do it, right? So I mean, I can extend. I don't know. You do want a new definition? So I can say this, right? So I have an xn belonging to t delta n. Sorry, I have an xn belonging to xn. What am I doing? I'm defining t delta n pxy given xn. Okay, the set of all those yn sequences such that x and yn are jointly typical. So I can write it this way, right? N of ab given xn yn, xn is fixed, divided by n minus pxy of a comma b is less than equal to delta pxy, that the normalization term with all of this, plus log cardinality of x, log cardinality of y. So I'm just being dumb by you ask me a question, I'm answering it, but possibly you're looking for something else. Next cross.
Yeah, I mean the definition involving p of y given x. I mean this probability distribution.
No, good point. I'm not doing that. It's a good point. So there are papers that are, I mean, there's another definition that you can, that typical set will be different, okay? I mean, to be very specific, that typical set is going to be different. I mean, to be very rigorous, it might have certain sequences that this doesn't have, and this might have certain sequences that doesn't have. I'm not giving that definition. I understand what you're saying. So, I could have defined this something like this: t delta n pxy given xn as all those sequences yn such that n of a comma b given xn yn divided by something, maybe n of a given xn, maybe, I don't know, minus py given x of b given a. This is within something. I could have done this, right? I'm guessing this is kind of what you're thinking. I'm not, good point, but I'm not doing that. Not a big deal really, but see, the thing is, when you if you define it like this, so in the properties you proved in the homework, I mean, you proved or you tried to prove, there'll be one thing that will be difficult, one or two things that will be difficult. If I define it like this, that particular statement might become easy, but some other statement will become difficult. So essentially they are equivalent. But I defined it like this, and I slightly prefer this. There's no big change. In terms of exponents and everything is it's going to remain the same. There will be some polynomial changes in the number of sequences and polynomials in the number of the exponents. I mean, the probabilities and things. It doesn't have any big consequence at the end. But I stick to this definition. I think Chisar and Corner take this definition, I'm guessing. Does that answer your question?
Yeah.
Yeah, I'm not sticking to this. I mean, I can give any definition I want, right? As long as I build my theory on my definition, everything is fine. So, I mean, he can build his theory on his definition. We're going to get the same result, but I feel this slightly more convenient. It's just, just got used to it. Is it okay?
Yes.
Okay, great. Yeah, feel free to ask. Okay, anything else? I showed this. Any other question, thoughts, ideas, comments, criticism, suggestions, remarks? Okay, so what I will do now, so it's telling you something. So what I will do, so let me now write some pictures. So what I will do, I will put all the typical xn sequences on the left. Clearly, I want to understand what's going on. there's some numbers and there are some inequalities and there's some confusion. So I'm going to try and understand what's going on. I'll do something interesting now. So what I'll do, on the left, I will put all the typical X sequences. List them, just put them in a list. Okay. On the right, I'm going to put all the YN sequences that are individually typical. That's all. Just individually, I'll just put them. Okay. Now, I will connect an edge between all those guys that are jointly typical. So if I take this guy, so if I take the first guy, right? I take the I take the first guy, right? I'm going to connect him to all the guys that he is jointly typical with. I don't know, maybe here, something like this. Okay, all those guys. I'm going to take the second guy and I'm going to connect him to all those guys that he is jointly typical with, possibly. I don't know. I'm going to take the third, every guy like that, and I'm going to, build something. Okay. How many edges will I have? First question, number of edges. Total number of edges. I claim it's going to be 2 power n h of xy because it's h of x comma y because there's the total number of jointly typical pairs. So the total number of edges will be 2 power n h of xy. Okay. I look at one guy. I look at one guy on the left. What is his out degree? He is going to be connected to 2 power n h of y given x number of jointly typical, yn guys. He's going to be married to so many guys, right? So this degree is going to be 2 power n h of y given x. Okay, so they're going to be, my picture is not very good, but yeah, so at least there's only one guy. So recall, it's going to have something like this, right? So if I look at the degree on the right, so if I look at a degree of a vertex on the right, it is going to be 2 power n h of x given y. Yeah. And I have no idea about, how they look like. They may be completely, they will be, obviously one fellow is, what do we have now? We have h of y given x is less than h of y. So that means that, I am taking a general circumstance. So that means that this, each fellow will not span the entire right side graph. It's going to be less. But at the same time, you see, if I so I'll just give one, one picture on the left that you can, another kind of a simple picture on the right that you can kind of, because kind of keep in your mind. Just for some clarity. So I'm going to do this. You see, they are overlapping, but there is some kind of a structure. You can see that the numbers are going to be slightly different. So what is in kind of what's happening on the left. So h of x, hopefully you got this nice. Okay. So h of x on the left, you can think of h of x as 5. I removed the exponent, just because things add up nicely. H of xy, the total number of edges is 12. Sorry, I think h of x is 6. 1, 2, 3, 4, 5, 6. H of xy, if you see, each fellow has 2 edges. So it is 2. So it is 12. H of y given x is 2. So each fellow has 2 outgoing edges. And similarly, h of x given y is 2. And h of y is also 6. Okay. This is a symmetric thing. I've taken a very symmetric case. So h of x is equal to h of y. H of x equal to h of y equal to 6. The out degree and the kind of the in degree, the out degree of both sides is 2. And we see clearly that h of xy is 6. I'm just trying to give you some intuition.
Sorry, I haven't got the interpretation of h of x given y and y given x in the diagram.
Yeah, good, good. Thank you. So see, what am I doing? On the left, I just simply forget everything. I simply listed all the xn sequences.
Yeah.
Typical xn sequence. Great. Okay, so maybe I'll set the stage properly. So I mean, I'm assuming this. So I have I have two sets x and y, and I have a joint distribution pxy. I can pull out marginals px and py and all that. Okay. Yeah. So now what on the left, what I do, I list all the xn sequences that are individually typical. I don't think about y at all when I do that. I go to the right, I list all the yn sequences that are individually typical. Then what I do, for each xn on the left, I mean, it's individually typical. So I will connect it to all those edges on the right that it is jointly typical with.
Yeah.
So all these all these guys are jointly typical when I put it with this guy. Okay. And similarly, so I take every sequence and I connect it like that. So how many sequences? So if I take one sequence here, how many sequences will it be connected to? It will be connected to exactly all those sequences which I can, if I marry it with that, it will be jointly typical, right? So this is going to be exactly T delta N Pxy given that sequence Xn, right?
Right.
That is 2 power n h of y given x, right?
Okay. Yeah.
That's what this is. That's the out degree. Similarly, if we go on the right and I ask, I get 2 power h of x given y. How many edges will I have? It is, I would have listed all, by doing this, I would have listed all the jointly typical pairs. They're all distinct. See, I have listed all the distinct sequence. I am not going to overcount or undercount or anything of that sort. So I'm going to have a total number of edges to be 2 power n h of xy, h of x comma y. Okay?
Yeah.
Okay, great. So comfortable so far?
Yeah.
Okay, great. So now let's see. I'm going to draw a more geometric picture. This is kind of a bipartite graph picture. I'm going to draw a more geometric picture. See, this intuition that I'm giving is very important. We'll build on this. I'll also quickly indicate one point that one of you asked. I think Soham asked, right? Why am I not doing? Why am I doing this and not doing this, right? It turns out when I go to the quantum setting, there is no notion of conditional probability, it turns out. So this definition doesn't hold water in that case. Okay, I mean, if you put it just like this, I mean, you can do something, but this is more, slightly more general. I am not really coming to the conditional element. So that's why I like this definition more. We'll come to it at a later point. But there are ways to overcome, I could go with the red one and still do it. But anyway. Okay, next. So I will now draw a more geometric picture. So let's take the T delta NPX. So now we know we're not going to get out of the, I'm not going to sweat and get out of the T delta NPX set. I'm not going to go to Xn because there's really no mass there. I mean, there's nothing need to care about it, though it's exponentially large. Okay. This is the T delta NPY set. Okay. Now, what I will do, I will take a sequence on the left. I will take sequences on the left, and I will, sequences on the right, and I will identify them with balls on the left that it is jointly typical with. So if I take the sequence 1, there is a ball with it that it is jointly typical with, right? That could be this ball. I take a second sequence, I take a second blue sequence, let's say I take second blue sequence, there's another ball. So, there's another ball. I'm going to just pictorially depict all those balls. They're going to be like this, right? All, they're not going to get out of the Xn space, the T delta N space, but they will be like this. Just a picture, okay? Similarly, I can do on the y space, right? I can go and so I take a point inside the x space, and I can list all those. I can write a ball on the right that are jointly typical with this black sequence, right? I can do that, right? So I'm going to write that ball. I'm going to write that ball in red. So could be this. I mean, I'm going to, yeah, it could be this, So all of these balls each ball is corresponding to the jointly typical set of one sequence on the right. Okay, so so I'll do this. So this is some t delta n of y given xn for some xn. This orange guy here is t delta n of pxy given yn. Okay, this is xy given xn. For some xn, that is individually typical. Okay, I will pause here because I need you to understand this before I go to the next step. So I will pause, have questions. I mean, ask your questions, clarifications, or doubts, or things that you don't believe, or you feel, hey, why should this be true or that be true? Just ask, because I'm going to make 3 statements, and from then we'll move on. Don't hesitate. I will ask one question. Don't hesitate. Put up your hand. How many of you are so far lost? If you're lost, I will just quickly tell you what's going on. But if you're not, I mean, if anybody is completely, I mean, little bit lost in the beginning, just raise your hand. I will try and quickly do some explanation. I'm not going to take too much time, but I'm going to quickly do. So don't hesitate. Let me know. But if you do understand, that's good. Okay. I'll pause for another 2 seconds. Observations, comments, remarks, suggestions. Okay. So now, how many orange balls are there? Okay. So number of orange balls. So before we go there, size of black ball. What is the size of black ball? Oh, I'll just write 3 questions. I'll not write the answers. You don't speak out the answers yet. Keep it in your mind, and then I'll tell you the answers. I'll write down the answers, and hopefully. So number of orange balls inside the black ball. I'll just, so that you see it. And size of an orange ball. Okay, similarly here, size of blue ball. Outer blue ball. Number of red balls. Size of a red ball. Really, we're doing this multiple times just to ensure that you get it in one way or the other. Size of the black ball. What is the size of the black ball? Okay, just maybe I'll wait for a couple of seconds for you to kind of think of these answers before I tell it out. You already know it, but just kind of reinforcing. So the size of the black ball is 2 power n h of x. There is no problem in that because just the individual typical sequences of xn. Size of the blue ball is also similarly 2 power n h of y. How many are so far with me? Put your hands up. So, okay, what happened to the rest?
I forgot how you raise your hand.
Huh?
Forgot how you raise your hand here.
Okay. See, I don't know. There should be something. I mean, I also wouldn't know. Okay, I will. So it appears. Sometimes I do this because I might be getting some parameters wrong. I mean, I'm sometimes I get some parameters wrong, and that confuses you, and you might not be getting it, and you might be silent because I made the mistake, and everybody doesn't know and things like that. This time I'm hopefully careful. Okay, so size of the orange ball. Well, it is I fixed a y. I'm looking at how many x guys, right? So that is going to be 2 power n h of x given y. Sorry, this is not the answer to that question. So the number of orange balls. Well, for every y, I have an orange ball, right? So it should not be difficult. It should be just 2 power n h of y. For every y, I have an orange ball on the x. So it has to be that. Size of the orange ball. Well, the size of the orange ball is 2 power n h of x given y. Because I take a y-n sequence, what does it blow up to on the x space? These orange balls are usually referred to as fan outs, okay? Even the red balls, they're called fan outs, and you can, how much it blows up to in some sense. The number of red balls. What is the number of red balls? Well, the number of red balls is 2 power n h of x, because for every x sequence, I pulled out a ball, right? I identified a ball. The size of a red ball is 2 power n h of y given x. Because I've chosen an x and I'm looking at how much it blows up. So observe the following. What's happening? So this clearly. So if I look at the number of orange balls, the size of the orange ball. So 2 power. So number of orange balls times size of an orange ball. So this gives me 2 power n h of x y. So, but the total size, they're all inside a size of 2 power h of x, and I know h of x y is greater than h of x. Remember, I did this remember this inequality here that I did? The h of x y is greater than h of x. So the intuition behind this inequality is that the uncertainty in x, y is greater than the uncertainty in x. I mean, the uncertainty can't, reduce. That's classical, okay? Sorry. So the uncertainty can't reduce. So, if I have too many fellows to understand, then it can't be that, I get a rebate, right? It appears. In classical. So in classical, this is true. So that means that these guys should be kind of, they should be overlapping. That's why I wrote it like this, very overlapping kind of a way. Similarly, you can multiply these two and you will see that they will overlap. Okay, they'll be greater than this. Okay. This is, everybody is okay with this picture? Those of you okay with this picture, put your hands up. I mean, do that handing thing. Okay. Okay, I take it that some of you are getting it. So now, what is packing? What is covering? I will put that question. That will be kind of the center of the entire course. That's why I want to be ensuring that you get this physically, because physically before you kind of formulate mathematical questions, right? So what is packing and covering? So you have balls that are overlapping. The number is a huge number, whatever. All these numbers are becoming clear. So what is packing? Okay, so I will state what is packing. So this is important. You will kind of see this through and through. When we go to quantum there'll be interesting things that happen. See, I've done kind of, so you see these three inequalities, you kind of use these inequalities, right? Kind of seeing this geometrically. You will see in the quantum, the first will hold. The first will hold in some weird sense. We do something slightly differently. The second will hold. The third, actually, we don't have a notion of conditional entropy at all in the quantum. It's kind of slightly weird. So this will not hold, which is very very non-intuitive. This will not hold. Okay. So that's why it kind of went it in one direction. You will see that I want you to see that change when you go to the quantum, and you will see some interesting things happen. That's why I'm taking some time to explain the intuition. Okay, what is the packing problem? The packing problem is the following. As you might be, the word packing will reveal itself. So what is the maximum? What is the maximum and identifying? Okay, packing problem, or let's say identifying a collection of red balls of well, again, I don't like this thing. Okay, let me not write it like this. Not a good. What is the maximum number of, what is the maximum, and the word maximum is important. What is the maximum number of red balls I can find within the blue ball that are important, disjoint? That's packing. Okay, so I want to find the maximum number of red balls that are disjoint in the blue set. So if you leave some space, you're not doing well, you should pack it. Okay, somehow. So you should maybe change your configuration, whatever it is, right? That's packing. They should be disjoint. And they should sit inside the blue thing. That is the packing problem. What is the covering problem? The covering problem is kind of the dual problem. What is the covering problem? What is the minimum number of I will make some remarks after I write it. Just kind of listen to it for now. What is the minimum number of orange balls that I can find? I'm going to reword this. This is not the best way to say it, but what is the minimum number of orange balls that I can find so that every element in the black ball is in at least one of the orange balls chosen. Okay, so I will kind of explain this. So what I want, so I have also done it, I could have done it in just one space. I could have written both questions in one space, but I'm doing it for a reason. You will, but these things will reveal itself. Why am I doing it in this order? These things will reveal it only at the end. Okay. So hold on. Okay. So what am I doing? Packing. Packing means I am trying to find a collection of red balls that are disjoint and that I want to find a maximum such configuration. That's packing. Okay, this is not a good packing because I need to fill up all the space, but possibly I can't add any more, at least in this configuration. Maybe this is not the best configuration, but that's the problem. Okay, that's packing. What is covering? So I want to find a collection and then identify the maximum number of that collection, maximum number in that collection, maximum, disjoint. Okay, so those are the two words you have to keep in mind: maximum, disjoint. The moment you remove one of them, it's trivial. Left side, I want to find the minimum number of orange balls so that every fellow is covered. Okay, so that's that minimum. So these guys need to go far as possible so that you're efficient. There they have to come near so that you can pack more. Okay, I mean, it's a bad, my thing is bad because it should not get out, but it's getting out. Don't pardon me for that. So again, it's not good because, but at least I should cover everything. Okay, so I have to choose one collection that covers everything. Okay, that's covering. So it's minimum here. I don't know, for some reason I'm doing it the other way around. Minimum here and covers the entire space. Okay, we'll get answers, we'll prove them. What is the guess? Let's look at the guess. So packing, answer. What do I guess? So far with me? How many of you are not put up your hand? I haven't gone too much from the last time, that's why I'm asking the reverse question. Okay, so what can I expect, right? So well, not really hard. So what is the blue? This guy, what is the size of this guy? Well, the size of, sorry, it's a P of y. These kind of mistakes I make, so I don't want to, I want to ensure that people don't get confused. So what is the size of this? This is 2 power n h of y. What is the size of a red ball? So if I take a red ball, what is the size? So T delta n of pxy given some xn guy. What is the size of this? This is 2 power n h of x given y. Sorry, y given x. Right? So clearly, trivially, you cannot have the disjoint. Remember, disjoint. You have to be disjoint. Okay. So clearly, I can't go beyond 2 power n h of y divided by 2 power n h of y given x, because each fellow is going to take up that space, right? You can't strip him of that space. It takes so many guys. Once you take it, gets out of the damn thing. Then you put one more. You can't get more than these, right? So this gives me 2 power n h of y but it's not clear I can get so many, because I have to ensure that what remains is exactly one ball, right? That's not clear because that guy might overlap. If that guy overlaps, then I have to leave that guy also. So then I might not get this number. So while it is clear that you have to get less than so much, your packing number cannot be, you're looking for maximum, you can't shoot for too much, has to be at most this. This is very clear, right? Let's look at the covering number. Well, covering each fellow, right? Let's look at this guy. Covering, right? So covering. So T delta n px, I have to cover so many. I can't do anything less. So this is 2 power n h of x, right? Each fellow, what is the size of each orange ball? It is 2 delta n pxy. I know I'm confusing you by going other way, this way and that way. You will see it has a reason in the quantum. So it doesn't have any reason in the classical, but you will see, it has some kind of reasoning. There's nothing, okay, it's all symmetric. I could have done everything on one side, nothing would have changed. But I'm doing it this way. You will see nothing will change actually, but still I'm doing it this way because something interesting happens when we go to quantum. Okay, and I want you kind of keep that distinction. Just see it in that light. So this turns out to be 2 power n h of, sorry, I made a mistake here. This is yn. So this turns out to be 2 power n h of x given y, right? So each fellow is only going to pull so many from that thing you want to cover. So many guys, you have to, mark each one of them. Each fellow will mark only so many. So you cannot have your covering number to be smaller. Maybe they overlap badly and you need too many more, but you cannot have them to be lesser than 2 power n h of x divided by 2 power n h of x given y. So this is 2 power n h of x minus h of x given y. Okay, tell me if you don't understand something. Questions, thoughts, remarks, comments, trivial, simple, too easy. This is like baby's game.
hx minus h of y given x, it's the mutual entropy, right?
I haven't told you anything so far.
Okay.
Yeah, we will come to it.
Is there motivation for these problems in like real world, or I mean,
Yeah,
in
absolutely.
theory
Actually,
was motivated by like communication or something, right? Initially. So is there some counterpart, for these specific problems?
yeah, we'll just do that. Good that you
Okay.
asked. Soft packing happens to be a communication problem. Deterministic packing happens to be, more general mathematical statement, but soft packing is completely a communication problem. We'll do exactly that today. Today, I have not today, but tomorrow.
Okay.
Yeah, these are completely motivated. Actually, uh, no information theory course will do it this way. They'll do it from the communication point. They'll say this is a communication problem. It turns out to be we are doing, and they're not going to mention packing at all, but I'm going to do it slightly differently. So I'm going to say packing first, and then I'm going to say, it has a communication thing, but don't worry about communication. Something more interesting also happening. That's how I'll go. But yeah, perfectly. Okay, so we'll make some more observations. So good, these things are good, nice. See, the intuition is important. Tomorrow when you do research, you won't have a theorem to prove. You have to identify what theorem is to be proved. So you need to make a guess what to try and prove, what to ask, what question to ask. So you need to try and guess what to ask, right? For that, you need to have the physics pain. I don't think you can just, be solid in inequality. Inequalities only come when you are trying to prove something. But that's the difference between a course and research. In course, you're given, you show this, you go show it. But in research, you will not be given what to show, and it's not clear what to ask. That's why I'm kind of going in that geometric way. So that's why it's important to have both perspectives. Strong in math, but good in ideas. Okay, next. So let's understand. So let's see. So we got one term, h of y minus h of y given x. And the other term we got was h of x minus h of x given y. Right? Turns out these two are equal, right? Because why are they equal? So if I add h of y plus h of y x given y, I get h of x plus h of y given x, right? So, I mean, I know this is confusing, but this is what it is. H of x, y, I can write it this way or that way. What I've done is, if you see, this guy has gone here and this guy has gone here. So these two terms are equal. Okay, these two terms are equal. So we will define. Suppose Pxy is a joint PMF on x cross y. Then we define the mutual information between x and y to be I of x colon y. This is how we write it, okay? H of x minus h of x given y. I can give you 3 formulas for this. Or you can check this out, not a big deal. I mean, I've just taken the second term and writing it as a difference, okay? So you see that this is positive. Why? Because we kind of saw this. This is by subadditivity. So this guy is positive. So that's one thing. Something interesting happens in the quantum, okay? You will see that come later. I did it in kind of this way, but something interesting happens. Okay, so now, so this is that. So now we will show that you can find so many red balls inside the blue ball. That is, you can hit the limit. That's the main theorem. And similarly, you can hit the limit here. Okay, you can hit the limit here. So you can go as down as that. You don't need more than that. You can go as high as this. Okay, so that is the problem. And now what is the why somebody cares about this problem? So we'll come to the communication problem. So the idea is the following. So what is the communication problem? Why is the packing problem interesting? Why is the covering problem interesting? Just a little bit, and then I'll go into the proof. Okay, I'll do soft packing. So what is, deterministic packing? Deterministic packing is that identify a C. This is a collection of all sequences inside Xn. It's a sub collection, it's a sub collection of sequences in Xn, so that so that given delta positive, we have T delta n of Pxy given. I'm not being very formal here, but I'll explain. Sorry, is empty, right? Sorry, is empty. So this intersection is empty for all M disjoint pairs, disjoint choices, M hat. Among all such connections, identify the one with the largest number. With the largest. Identify the largest such collection, right? That's your deterministic packing problem. So that's a deterministic packing problem. I'll come to the communication problem, and that'll reveal itself as a soft packing problem, and we'll go ahead and solve that. Okay, and just formally. Okay, so the idea is the following. In communication, right? What happens is, see, you send. So just think of an antenna here and an antenna here. Okay. Okay, so we send a signal. So we, to communicate bits, right? You want to communicate 0 and 1. We choose one signal. Let's say we choose one signal for 0, and we choose, say, we choose some other signal. Okay, let's say this signal. Okay, so this signal is 0. If I send this signal, it means 1. I put it on the air, it goes that side. And there's an antenna there that receives the signal, and it will do some, it will try to figure out what was sent, right? If everything was perfect, then, if you send this signal, you get that signal as is. If and you you send this, weird looking signal. I don't know why I wrote it like this, but if I send this, then it goes as is, everything is good. But doesn't work like that. There is too much of perturbation due to the receiver electronics, multi-path fading. You see multiple things get added with different phases, and all those things happen, and you will end up with a signal that is kind of like this. I mean, not like this, but some weird signal. Okay. How do you decide what is it? So you, at the receiver, you have to say, whether it was 0 or 1, the signal corresponding to 0 or 1 was sent. So what you do generally, okay, I mean, I'll give you the model. So so this is some duration t. This is some, it's a t second duration. This is also a t second duration. You receive this. What you do is you kind of partition your space of received signals into 2 parts, okay? If it falls here, you will say, okay, it was possibly this was sent. If it was this, you would say possibly it was this weird signal that was sent. So you partition it. This partitioning you can go and improve, okay? But the idea is you take some partition and you work with it. So what this does is it establishes an end-to-end stochastic transition. So once you fix your signals, you fix your partitioning, then what it does is it sets up an end-to-end probability, right? So this guy is, going to, when he sees 0, he's going to send the signal. That guy is going to, whenever he sees something, he's going to make a call, right? So it ends up setting a stochastic matrix between what you send and what you receive. Okay, it puts some law. You can try and improve that law, but beyond a point, you can't improve it. You have to live with that law that nature gives. You can try and understand that law, but you have to live with it. It's not that, you can change that beyond a point. Okay. So the question is how many bits we can communicate per signal transmission reliably. That is the question we ask in communication. So this guy is fixed. It's known, it's fixed. You can't change it. It behaves like that. And you want to ask the question, how many bits can I communicate reliably? I'll give you an example. So suppose, the thing that you have to live with, it's a very bad thing. You're sitting in the tunnel and you're trying to communicate with the base station, and the transition looks like this. So that is, if you send 0, with say probability 0.2, it's getting flipped. Okay, it's a huge probability. I mean, just imagine if you send bits and with 0.2 probability it gets flipped. I mean, nothing will go. So it's getting flipped. So now the question is, what do? You can't live with 0.2 probability, right? You have to try and somehow squeeze it down. So this is your channel matrix, right? This is your channel law. And you want to kind of, somehow do reliable communication. And that's where this packing problem will come. What is the packing problem? The idea is, okay, don't communicate, if you communicate individual bits, it's crazy, right? So there is a now think of, trying to build redundancy in your code. So clearly, if you see, observe the following. Suppose I send 0, let's say 7 times. Okay, and 1 7 times. So if I want to send a 1, I'm not going to send it once. I'm going to send it 7 times. Okay, so 1, 2, 3, 4, 5, 6, 7. If I get a 1, I'm going to send it 7 times. Okay, that fellow uses a majority logic decision. So if he sees whatever he sees 4 times, 4, 5, 6, 7, he'll decide that. So if he has to get either 4 zeros or 4 ones or 5 zeros or 5 ones, one of the two. So he is going to decide that way. So then you're asking, you're challenging the damn channel to flip more than 4 times, right? So the channel has to sweat. He was splitting, the channel, if you see, the channel is flipping once in 5 times. Now, out of 7 times, he has to flip 4 times for you to make an error. So you're kind of, challenging the channel. It's called a very simple repetition code. It's trivial. But what you're doing is you're taking now a 7 dimensional space right? And you're choosing 2 points that look really far apart so that those the high probability balls corresponding to this, right? That is going far apart. They're not disjoint because there is a probability that it'll go there, but this is what you're trying to do. Okay. So, but you're just choosing 2 out of 2 power 7 possibilities, right? You get some probability of error. You want to drive that probability of error down to 0. I mean, think of using this communication for controlling some sensitive plant somewhere. And if you're relying on channel to be benign to you, it may not work out. So you have to drive the probability down to 0. But then that means you have to take, maybe, x power, I don't know, maybe 140, 150, and you take 2 bits. I mean, 2 possibilities. You're paying in power. So this is the problem. So you're trying to isolate these guys, but you're not ambitious. You're just saying, 2 points, right? That is when the packing problem comes. What is the maximum number of balls I can get so that they are disjoint? So that is the packing problem. So remember that what is T delta N? Go back to your homework. What is T delta N Pxy given Yn? If I put Yn through this stochastic matrix, remember this? So I will put it in you look back at your homework and you will see this problem. Xy given Xn, right? So if I fix my Xn and I generate my sequence according to this distribution, that's one of your problems. Then the probability that I will be in my typical set, Yn belongs to T delta N Pxy given Xn, this is very large. So if I choose an Xn and I put it on my channel, that's my channel, right? I take a typical Xn, I put it on my channel. That means what? I'm X1, X2, X3. I'm activating my antenna with those X1, X2, X3. I put it on the channel. The probability that I will fall in that corresponding conditional typical set is very high. So now if I can find many such sequences, let's say Xn of 1, Xn of 2, Xn of 3, many such sequences, Xn of something M, so that the conditional typical sets of each one of these fellows are disjoint, right? Intersection, the other thing is disjoint. That means that I am forcing nature to put outputs in disjoint sets. So that means somebody who is observing this Yn, he can just say, oh, it is in this ball, okay, it is this point. If it is in this ball, it is this point. They are never overlapping, so things are fine, right? So do you understand this connection? It is important.
Yeah.
Important in the sense that, you can just do the math. In which case, the packing problem is a well-defined problem. But if you're trying to connect it to information, if you're trying to connect it to communication, this is exactly how it started out with. But I'm doing the other way around, okay? So this was 1948. And Shannon, I don't know whether Shannon, yeah, maybe, I don't know whether Shannon really completely identified this as a packing problem, or later people recognize that, okay, this is really packing. But that's really what is going on. So if I solve the packing problem, that collection becomes what is called a code. That's why I'm using the word C. That collection becomes a code. So that means that each element in that C is called a code word. Okay? So each code word becomes a information carrier. So in some sense, if I get a particular bit sequence, I'll put it to that code word. I get a different bit sequence, I put it to a different code word. So then that fellow will be the guy who receives it. He will see it in disjoint balls, and he'll recognize which bit sequence came from there. This is exactly what we use today in all our systems. packing has more interesting things. You go to quantum, you will see packing. You go to physics, you will see packing. You go to math, you will see packing. So if you see one of the, I think 2-3 years ago, not 2017 or 18, one of the important medals in mathematics, right, was given for 24-dimensional packing, for solving a 24-dimensional packing problem. There's a lady from Ukraine, I think. So yeah, this has, that was deterministic packing. Here, Shannon did soft probabilistic packing. Later, we'll go to deterministic packing. Chizal does a little bit of deterministic packing. Okay, is the connection to communication making sense? How many of you did the connection to communication make sense?
Yeah, it made sense.
Okay. So I'm out of time, right? I wish to cover more, but I had the entire packing proof to complete, but I could not. That's okay. But the intuition is important. So this I of xy is a very important object. That is your mutual information term. This will also manifest in the quantum setting. To just give you a sense of what happens in the quantum, just to pique your interest in the quantum setting, what happens is here we are packing subsets in subsets in subsets. In quantum, we'll be packing subspaces in subspaces. Okay, you'll be packing disjoint becomes orthogonal. So you'll be packing orthogonal subspaces in a bigger subspace, and then you'll be trying to cover a bigger subspace with orthogonal subspaces. That becomes the quantum covering problem. This becomes a quantum packing problem. You will see similar objects, but it turns out there will be some asymmetry, which is fundamental. So that will come later. There will be different levels of packing. There will be quantum, there will be a CQ packing, there will be a QQ packing, and all of that. So in the next class, we will prove the packing. So we'll prove the communication soft packing. After that, I'll come to the quantum, I'll come to the covering. And in the covering, you'll get a dual problem. Yeah, it's very beautiful. Okay, so a lot of things I have to tell you. Yeah. Sorry. Yeah, please say it once again. The network was bad.
I have another class at 6:30, so
Yeah. So we'll end now.
I have another class now, so I'll leave.
Yeah.
Yes, sir. Me too.
Yeah. So please, one of you relay this to the others. Just fill up all the day's sheets starting from tomorrow. Tomorrow class will be at normal time. And we will. I think I'll have a class. I mean, tomorrow and after tomorrow we'll have class at normal time. We might have an extra class on Sunday. I will post an email for office hours.